The last topic we need to cover in our study of series is absolute and conditional convergence. Let's go ahead and define both of those terms. Number one, the series A sub k is absolutely convergent, provided the series of the absolute value of A sub k converges. So to assist your intuition in understanding this concept, think about it this way. This is an alternating series. So I'm going to take away the alternation by finding the absolute value of the terms. This series is the sum of positive terms only. If the sum of the positive terms converge, then that must mean that the alternating series converges because this is composed of both positive and negative terms. Because of the different signs throughout that sum, you'll get more cancellation. This series will converge faster than the sum of only positive terms. Let's look at definition number 2. The series A sub k is conditionally convergent if the alternating series converges, but the absolute value series diverges. So it's still possible that if I take the absolute value of those terms, creating positive terms only in the sum, yielding a divergent sum, it's still possible that if we allow the alternation in sign term to term, that the alternating series will still converge. Once again, you get cancellation based on the fact that you have positive and negative add-ins in that sum. In the previous example in our last video, we can conclude that the harmonic series is conditionally convergent because the alternating harmonic series converges while the normal harmonic series, or the absolute value of this one, diverges. So the only way that we can get a sum that resembles this to converge is to allow it to alternate. If every other term alternates in sign, then the sum becomes finite. If we look at just the sum of the positive terms, that sum diverges. So the harmonic series, the very interesting harmonic series, is conditionally convergent. Now, this is going to add some convenience to our work in examining the positive form or the absolute value form of our alternating series. Here's a theorem that will be helpful. Number one, if the series of the absolute value of A sub k converges, then the series A sub k, which is an alternating series, also converges. Once again, the idea is simply that this sum is going to be bigger because it's composed of positive add-ins, bigger than this sum because it is composed of both positive and negative add-ins. So there's a little bit of cancellation that occurs as we sum this alternating series. So if the bigger sum converges, then naturally this one will converge as well. In practice, what this means is that I can avoid the alternating series test by examining the absolute value form of the series. If that one converges, then I can conclude that the alternating series also converges. In addition, number 2 says if the alternating series diverges, remember this is the sum of positive and negative terms, if the positive and negative is not enough to cancel out the sum so that it converges, okay, if the alternating series diverges, then the absolute value form of the series must absolutely diverge, right? Because it would be a larger sum. A sum composed of all positive add-ins is going to be larger than a sum composed of positive and negative add-ins. So keep these results in mind as we examine example 5. Determine whether the following series converge absolutely, converge conditionally, or diverge. The first one I'm going to check is absolute convergence. If I can show that the absolute value form of the series converges, then it is absolutely convergent. So we'll begin there. Let's examine the series from k equals 1 to infinity of the absolute value of negative 1 to the k times k over 2k plus 1. Now remember, this -1 to a power is what causes it to alternate in sign. In odd values of k, that's a negative number. In even values of k, that's a positive number, +1. So the absolute value causes them all to be positive. So we can simplify this by writing it as the sum from k equals 1 to infinity. The -1 to the k will always be +1, so we can drop that. K is always positive, and 2k plus 1 is always positive, so we don't even need the absolute value bars. Now, looking at the absolute value form of this series, we need to choose a test where we can establish convergence or divergence. Remember, one of the first tests that we learned was the divergence test. So if we find the limit as k goes to infinity of k over 2k plus 1, we find out it's 1/2. Remember, the results of the divergence test, we just want to see, is the limit different from 0? And in this case, it is. So the divergence test indicates that the absolute value form of this series diverges. So we'll make a little mini conclusion here. By the divergence test, the series absolute value of a sub k diverges. So at this point, we can rule out absolute convergence. Either this series converges conditionally or it diverges altogether. So I'm going to go back to the original series, that is the alternating form of the series, and we want to apply the alternating series test. So we're looking at the sum from k equals 1 to infinity of -1 to the k times k over 2k plus 1. Now there's two things that we need to verify for the alternating series test. First of all, notice that k over 2k plus 1 is non-increasing. Okay, translation, it's kind of decreasing. In fact, it is decreasing. Non-increasing means it's either decreasing or staying the same. We can tell just by looking, because notice, as k approaches infinity, as k increases, the denominator is always bigger than the numerator. The denominator is growing faster than the numerator. That means that our function is decreasing. So that verifies the first component of the alternating series test. The second component is that we have to show that the limit as k approaches infinity is 0. So we find the limit as k approaches infinity of k over 2k plus 1. We find out it is not 0, but 1/2. Since this second tenet of the alternating series test didn't pan out, remember both of them have to be satisfied, we could say then the alternating series diverges by the alternating series test. That means we can rule out conditional convergence, and our conclusion is that the original series altogether diverges. So you may be wondering, why did I have to check the absolute value form of the series before applying the alternating series test? Well, in this case, it didn't save us any time. But remember, if I find out that the absolute value form of the series converges, that naturally implies that it is absolutely convergent. So when it works out efficiently. But in this case, it was a little more work than usual. All right, let's try example B. We want to know, is it absolutely convergent, conditionally convergent, or does it altogether diverge? So the first thing I'm going to examine is the absolute value form of our series. We'll look at the sum from k equals 1 to infinity of the absolute value of -1 to the k times k squared over the square root of k to the 6th plus 1. Well, of course, the absolute values will eliminate the -1 to a power. That will always turn out to be +1. K squared is always positive, and the square root of k to the 6th plus 1 is always positive. So we can even drop our absolute value bars. So looking at this series with fresh eyes, because it's a little different than the original, we now need to choose an appropriate test. First thing that pops into my mind is the divergence test. If I take a limit at infinity, notice because the degree of the denominator is bigger than the degree of the numerator, the limit is going to be 0. So the divergence test is inconclusive. The next thing we might try is maybe a comparison test. Let's try a limit comparison test. So this is going to be similar to the series from 1 to infinity, and I'm just going to take the leading terms in both the numerator and the denominator. If we reduce this, we have k squared over k cubed, or our very famous harmonic series, 1 over k. This is definitely divergent. So we want to compare our original, or the absolute value form of our series, to our divergent harmonic series using the limit comparison test. Remember the details of the limit comparison test. We need to find the limit as k goes to infinity of the given series, that's the absolute value form of our series, divided by the one we're comparing it to, the harmonic. So let's clean up our complex fraction here. We're going to invert that denominator and multiply. Multiplying our numerators, we have k cubed over the square root of k to the 6th plus 1. Now, thinking carefully about this, notice the degree of the numerator is 3, and the net degree of the denominator is also 3. Now, where did I get that? When I'm calculating a limit at infinity, I only need to consider the leading power functions in both the numerator and the denominator. So I'm only thinking about what does the square root of k to the 6th do? If I add 1 to infinity, it doesn't make a difference. So when we simplify the square root of k to the 6th, that's k to the 6 over 2, or 3. So ultimately, on an infinite scale here, the numerator and denominator are equivalent, or they at least have equal degrees. So we can conclude that this limit is 1. Now remember, we are in the context of the limit comparison test. If I were doing ratio test or root test, then a limit of 1 would give me an inconclusive test. But we're in the context of the limit comparison test. So what am I looking for when I do the limit comparison test? I'm testing to see if this limit is positive and finite, and it is. Since it's positive and finite, that indicates that the series in question will have the same behavior as the series we're comparing it to. Since the series we're comparing it to is the divergent harmonic series, then our original series is also divergent. So we can say that the absolute value form of this series diverges by limit comparison test with the harmonic series. So at this point, we can rule out absolute convergence. It's kind of a bummer whenever you find out that the absolute value form diverges, because that means you need to test for conditional convergence. So I'm going to go back to my original series and apply the alternating series test. So now we're considering the series, the original series from 1 to infinity of negative 1 to the k over the square root, k squared up there too, square root of k to the 6th plus 1. There's two things that we need to verify. First of all, we can see very obviously that a sub k is non-increasing. Now, how do we know that? We could establish an inequality, we could use a derivative, or we could simply see the denominator is of greater degree than the numerator. Remember, I'm just looking at the a sub k part, right? And from our analysis right here, we can see the degree of the denominator is 3, the degree of the numerator is 2. So because the degree of the denominator is greater than the numerator, as k increases, we have a decreasing fraction. So a sub k is non-increasing. So the first tenet of our alternating series test has been satisfied. The next thing we need to do is find the limit as k goes to infinity of a sub k. So we have k squared divided by the square root of k to the 6th plus 1. Now, once again, the degree of the numerator is 2. The degree of the denominator is 3. Again, different up here because remember we had multiplied by k, so this time we have a lesser degree in the numerator. If the degree of the numerator is less than the degree of the denominator, then the limit is 0. So we have verified both parts of the alternating series test. It's non-decreasing, the limit of a sub k is 0, so the alternating series test indicates that the alternating series converges. So therefore, the series from k equals 1 to infinity of negative 1 to the k times k squared over the square root of k to the 6th plus 1 converges by the alternating series test. So, to answer the question that was posed, because the absolute value form is divergent, but the alternating form is convergent, this is an example of a series that is conditionally convergent. So it's in the same boat as the harmonic series. Okay, one more example for all of Chapter 9. We want to determine if this is absolutely convergent, conditionally convergent, or divergent. So we're going to start by examining the absolute value form of this series. The absolute value of negative 1 to the k is just 1. And because k is always positive, the cube root of k is positive, and the square root of k plus 5 is positive. So we can drop those absolute value bars. Looking at this with fresh eyes, we need to figure out a test to determine if this absolute value form of the series converges or diverges. Now, a quick glance would tell us that the divergence test would fail, so I'm going to go for limit comparison test again. This will be similar to the series from 1 to infinity of the cube root of k, and I'm just taking the leading term in both the numerator and the denominator. So let's see if we can figure out what this guy does. If we rewrite this as k to the 1/3 divided by k to the 1/2, then we can simplify by subtracting those exponents, right? Dividing like bases, we subtract the exponents. Now, 1/2 in the bottom is bigger than 1/3. So when we subtract, the leftovers are going to be in the bottom. 1/2 minus 1/3 gives us 1/6. So hopefully you recognize this as a p-series. In this case, the p-value is 1/6. It is less than 1. So we are dealing with a divergent p-series. So we're going to take this series and apply limit comparison test with this series. So in our limit comparison test, we're going to find the limit as k goes to infinity of the given series, which, by the way, I'm going to write with rational exponents. And we're going to divide by this one. If we're dividing by a fraction, we know that's the same thing as multiplying by the reciprocal. So combining our powers, we have the limit as k goes to infinity of k to the 1/3 plus 1/6, or 2/6 plus 1/6, that'll give me 3/6 or 1/2, divided by k plus 5 to the 1/2. Since the degree of the top is equal to the degree of the bottom, the limit is the ratio of leading coefficients, which is 1. Now remember, we're in the context of the limit comparison test, so we're observing that this limit is positive and finite, which means the series under question is going to exhibit the same behavior as the one that we're comparing it to. So the series of the absolute value of a sub k diverges by limit comparison test with a divergent p-series. Bummer, I was hoping we would get one that's absolutely convergent. By the way, at this point, if we found that it converges, we wouldn't even have to look at the alternating series test. We could say the whole thing's absolutely convergent. But we do have to go back and apply the alternating series test to the original. At this point, we're testing for conditional convergence. So I'm thinking about all the details of our alternating series test. There's two things that we need to verify. First of all, looking at a sub k, and again, I'm going to write it with rational exponents because the degree of the denominator is bigger than the numerator. We know that this is a decreasing function, or we could say, to be specific, this is non-increasing. So the first tenet of the alternating series test has been verified. The second thing I need to do is find the limit as k goes to infinity of k to the 1/3 over k plus 5 to the 1/2. Now, it kind of feels like we're repeating ourselves here. Remember, the details are a little different than what we did up here because our exponents are different. But we can see the degree of the denominator is bigger than the degree of the numerator, so the limit is 0. So that is the second tenet of the alternating series test that has been verified. So we can say the given series converges by the alternating series test. So to answer the big question that was posed, is this conditionally convergent, absolutely convergent, or does it diverge? Well, the absolute value form of the series diverges while the alternating form converges. Therefore, this series is conditionally convergent. So this completes our study of series in Chapter 9. So congratulations, you are a master of integration, and now you have quite a bit of experience with series. Both of those techniques will pay off whenever you get to your future math classes, especially differential equations.